Let's dive right in, shall we? You know, we use numbers literally every single day, but most of us never really stop to grasp their hidden depths. Today, we're exploring the ultimate mathematical family tree in this explainer covering Chapter 2, Real Numbers. If the abstract side of math sometimes feels a bit like a foreign language, don't sweat it. By the time we wrap up, these numbers are going to feel like old friends. So let's expand our mathematical universe together.
Here is our roadmap for today. First up, the family of numbers. Second, rules of the rational club. Third, cracking the decimal code. Fourth, meet the irrationals. And finally, taming the denominator. Let's get to it.
All right, part 1, the family of numbers. Let's see how these sets naturally nest right inside each other.
Okay, so you've seen those Russian nesting dolls, right? You open the first one, there's another inside, and then another. Well, the story of numbers works exactly like that. The smallest, innermost box is the natural numbers, represented by n, which just holds your basic counting numbers, things like 8, 12, 105. Now, if we toss a 0 into the mix, boom, the box expands. Now we've got whole numbers, or W. But obviously, math doesn't stop there. If we throw in negative numbers, like -1, the box grows again into integers, which we call z. And finally, if we start filling in the spaces between those integers with fractions, say -1/2 or 3/7, that entire collection becomes rational numbers, or Q. So the big takeaway here is that every new set is basically a container that swallows up all the previous ones.
And when you bring all of these different groups together, you get our ultimate mathematical collection, real numbers. This is the giant umbrella that covers everything. It holds all our predictable, well-behaved rational numbers, plus the completely wild, rule-breaking irrational numbers that we'll be talking about in just a minute. These real numbers literally account for every single microscopic point on the entire number line.
Moving on to part 2, rules of the rational club. Let's look at how these numbers actually behave.
So, let's focus on the rational numbers for a second. Imagine them as this exclusive VIP club. And like any VIP club, it has a very strict entry policy. In math, we call this the closure property. Think of it like this. If you add two rational numbers together, your answer is also a rational number. You pass the test, you get to stay in the club. It's a solid yes for addition, subtraction, and multiplication. But division? Division completely fails the test. Why? Because if you try dividing any rational number by 0, the whole system just breaks down. 0 is essentially the club's bouncer that absolutely denies entry for division. It's a great reminder that every mathematical operation has its own unique temperament.
Now check out these two rules, the commutative and associative properties. The commutative property basically says that order doesn't matter at all. 2 plus 3 is 5, and 3 plus 2 is also 5. You can just swap the numbers around, no problem. The associative property, on the other hand, is all about how we group things. If you're adding three numbers, whether you group A and B first or B and C first, the final outcome is exactly the same. So one is about shuffling the order, and the other is about grouping. These rules are absolutely crucial because they're the foundation of algebra. They make our calculations infinitely easier to handle.
And inside these rational club, we have two absolute legends, 0 and 1. 0 is our additive identity. If you add 0 to any number, it doesn't change that number's identity at all. 1 is our multiplicative identity. Multiply anything by 1 and it stays exactly as it is. I know, it sounds incredibly obvious, right? But believe me, when you start solving massive, complex equations later on, the superpower of these two identities is an absolute game changer.
All right, Section 3, cracking the decimal code. Let's unmask some complicated fractions.
Every so often, a simple rational number will try to disguise itself as a messy, never-ending decimal. So how do we crack that code? We use this brilliant algebraic magic trick. Let's say you've got a number like 73.456456 that just loops forever. It actually is a rational number, it's just not written in a nice, neat P over Q fraction format yet. Here's what we do. We simply call this number x. Since there are three digits, the 4, the 5, and the 6, caught in this endless loop, we multiply both sides by 1,000. Now here's the genius part. When we subtract the original x equation from this new one, that entire never-ending decimal tail just completely vanishes. Poof! You're left with a perfect fraction. It's literally like ripping off a disguise to reveal the clean rational number hiding underneath.
Part 4, meet the irrationals. Time to look at the numbers that refuse to play by the rules.
Up until now, everything we've looked at follows a pretty strict framework, but the math universe isn't always so well behaved. Enter the irrational numbers. To be part of this rebel group, a number has to meet two strict conditions. First, its decimal expansion has to be non-terminating. That means it literally goes on to infinity. It never stops. Second, it has to be non-repeating. No patterns, no fixed loops. These numbers absolutely refuse to be squeezed into a clean p over q fraction. They are 100% unpredictable.
I mean, just look at the sheer visual chaos here. Take pi, for example. We all know pi starts with 3.14159, but then it just keeps going, millions, billions of digits without a single repeating pattern. Or look at the square root of 2, 1.414213, and it just splinters off into totally random numbers. There is absolutely no way to tie these down into a simple ratio. And honestly, that wild, untamed nature is exactly what makes studying them so fascinating.
Finally, Section 5, Taming the Denominator. Let's solve a major mathematical headache.
So, picture this nightmare scenario. You're working on an equation, and one of these wild irrational numbers gets stuck at the bottom of a fraction. It's in the denominator. Look at this example, 1 divided by the square root of 2. How are we supposed to divide the number 1 by a number that literally never ends and has no pattern? Trying to divide by 1.414213 is impossible. Technically, you can't even start dividing until that denominator is fixed. We have to tame it. To get past this roadblock, we use this incredibly elegant technique called rationalizing the denominator. We take our problem fraction, 1 over the square root of 2. Because we desperately need to kill that square root on the bottom, we multiply both the top and the bottom by the square root of 2. And remember our identity rules from earlier? We're basically just multiplying the whole thing by 1, so we aren't changing its actual value. What happens next is amazing. On the bottom, the square root of 2 times the square root of 2 magically snaps into a clean, simple 2. The top just becomes the square root of 2. So our final, tamed answer is the square root of 2 divided by 2. We successfully fixed the denominator. Now it's a manageable problem. It's just pure, brilliant logic. So, let's take a step back. We started our journey today with basic counting numbers. We brought in 0, played with fractions, decoded the irrationals, and mapped out the entire universe of real numbers. But I want to leave you with something to chew on. If this universe of real numbers extends out infinitely, is that literally everything? Or are there hidden dimensions of mathematics still waiting out there? Perhaps a place where numbers exist that aren't even real at all. I really hope this explainer gave you a solid, intuitive grasp of Chapter 2 and the real numbers family. Hold on to these concepts, because literally all of your future math is going to build straight on top of this foundation. Keep questioning, keep exploring, and we'll catch you in the next one.